domain and range. For any relation, the set of values of the independent variable or often the x values, is called the domain of the relation. So the set of independent variables, which are usually the x values, is the domain of the relation. The set of corresponding dependent variables, often the y values, are called the range of a relation. So the set of corresponding dependent variables, often the y values, are known as the range. In a function, each value in the domain corresponds with exactly one value in the range. If a value in the domain has more than one corresponding value in the range, then the relation is not a function. So if it is a function, if the relation is a function, then that means that each value in the domain has only one corresponding value in the range. If a single value in the domain has more than one corresponding value in the range, then that is not a function, and it is simply a relation. With this knowledge, you can determine if the relation displayed through a set of data is a function or not. For example, if you are given the set of ordered pairs -3, 4, 5, -6, -2, 7, 5, 3, 6, -8. If you're given this set of 5 ordered pairs, you can determine if any value in the domain corresponds with more than one value in the range, in order to determine if it is a function or not. So you're going to check if any value in the domain has more than one corresponding value in the range. In order to do this, you're going to rewrite this set of ordered pairs and express it as the domain and range of this set of ordered pairs. You're going to rewrite it and you're going to express it as the domain and range of this set of ordered pairs. First, find the domain and range of the entire set. So that's what you're going to do. The domain is the set of independent variables, or the x-coordinates in this case. So this is the domain. The range is the set of dependent variables, or the y-coordinates in this case. So this is the range. So we're going to write that down now, and we're going to start. So again, we're given the set of ordered pairs, -3, 4, 5, -6, -2, 7, 5, 3, 6, -8. And we're going to break that down into the domain or range of this set of numbers, of this ordered pair. So use curly brackets to enclose numbers in a set. Therefore the domain and range would be, and we start with the domain. We start with the numbers that are least, and we go to the numbers that are greatest. So for the domain, we want the x-coordinates. So we start with -3 because that's the smallest x-coordinate here. Then -2, so -3, -2, and then we have 5, and 5 appears in more than one. But we only list it one time because it's only one number. 5, we want all the numbers that appear in the domain. But we don't list it more than once because it's only one number. And we would just want the numbers that appear in the domain. So 5 and 6. 6. Next we do the range. We start with the least number. The least number out of these y-coordinates is -8. So we start with -8. -8, -6. -6 is the second smallest number out of the y-coordinates. So -6 is the second one. Then we go to the next largest number, and that would be 3. So 3 negative 8, negative 6, 3. Then we have 4, then we have 7. So we list them in that order. 3, 4, 7. Negative 8, negative 6, 3, 4, 7. So we took these y coordinates and we listed them in the order from least to greatest. So negative 8, negative 6, 3, 4, 7. Note how the numbers are placed in increasing order. Now compare we continue here. Now compare the number of terms in the range with the number of terms in the domain. There are more. So let's count. How many terms are there in the domain? 1, 2, 3, 4. There are only 4 terms, not 5. Like there are 5 points here. Because we only wrote the number 5 once instead of 2 times, if you remember. So instead of there being 1, 2, 3, 4, 5 numbers here, there's only 4 numbers in the domain. But in the range, there's 1, 2, 3, 4, 5 numbers in the domain. So there's 5 numbers in the range. So there's 4 numbers in the domain and 5 numbers in the range. If there are more terms in the range than in the domain, like there are here, then you know at least 1 term in the domain corresponds with more than 1 term in the range. There are more terms in the range here than in the domain because there's 5 terms in the range and there's 4 terms in the domain. So we know that at least 1 term in the domain corresponds with more than 1 term in the range. And if we remember which term that is, it's 5. Because there are 2 5s and they each correspond to a different term in the range. So at least 1 term in the domain, 5, corresponds with more than 1 term in the range. And as you can see here, 5 corresponds with negative 6 and it also corresponds with 3. So it corresponds with 2 terms in the range. Consequently, the relation is not a function. So this is, as a result, this is not a function. Let us look at our relation now. So we can say not a function. Not a function. Let us look at our relation now. So again, reviewing. Since there are 5 terms in the range, 1, 2, 3, 4, 5, and only 4 terms in the domain, 1, 2, 3, 4, the relation is not a function. So this is not a function. If the domain has more than or equal number of terms as the range, then the relation is a function. So if this domain has more terms or the same number of terms as the range, then the relation is a function. How could this have more number of terms as the range? How could the domain have more number of terms as the range? That could happen if 2 terms in the domain correspond with 1 term in the range. For example, if this was 5, negative 6, and then negative 2, negative 6 instead of 7, it would be 2 terms corresponding with negative 6. It would be 5 and negative 2 corresponding with negative 6. And you would have 5 and negative 2 in the domain, but you would only have negative 6 in the range 1 time, because you only list each number 1 time in the domain and in the range. So therefore the range would have 1 less number than the domain. The domain would have 1 more number, and this would be a function. And now, since we've reached the halfway point, let's go through a small commercial break so you know exactly what MyMathEducator.com offers you. MyMathEducator.com offers in-depth lessons based on the curriculum for a fee of $29.99 a year. If you want the same lessons from MyMathEducator.com offered in video format for free, simply go to our YouTube channel. Remember, if you want our math lessons offered in video format for free, go to our YouTube channel. If you want the same lessons in text format, go to MyMathEducator.com. Domain and range. The domain and range of equations can be expressed through set notation. The domain and range of an equation can be found by seeing what values cannot exist for the particular equation. So values that do not exist for a particular equation are excluded from the domain of that equation. These restrictions are then stated in the domain and the range of the equation. Restrictions on the domain include dividing by zero and when an expression under a radical sign is negative. These cases cannot exist. So, restrictions on the domain would include division by zero in an equation, or when the sign under a radical sign or a root sign is negative. When these cases occur, these cases are restrictions and must be excluded from the domain. The range of the function can be determined by the shape of the graph of the function. This is a function, and it is y equals x squared. It intersects the x and the y-axis at 0, 0. And it goes on in both directions, upward, and it goes on infinitely in both directions. For the graph above y equals x squared, there are no restrictions on the possible values of x. And in fact, x can be any real number, any rational, irrational number. This is because the graph goes on in both directions, horizontally, infinitely. Therefore, the domain is written as domain is x equals, domain is x belongs to all real numbers. This reads as the domain belongs to all real numbers. This sign here means belongs to, and R represents the set of real numbers. Always use curly brackets when denoting domain and range. Since the graph of the parabola has y values greater than or equal to 0, the range is as follows. And the graph of the parabola has y values greater than or equal to 0 because 0, 0 is the intersection point of the graph with the x and the y-axis. So it has y values that are greater than or equal to 0. And the y values go upward infinitely. So as a result, the range is y belongs to all real numbers, except that y is greater than or equal to 0. Y cannot be negative because the intersection point with the x and y-axis is 0, 0, and the graph goes upward infinitely. So the range is y belongs to all real numbers, y is greater than or equal to 0. Note the restriction on the range, which states that the y values must be greater than or equal to 0. So here we have the restriction on the range stating that y values have to be greater than or equal to 0. In some cases, a function has only one value in which the domain or range is restricted. This is known as an asymptote. So when there's only one value which the x values cannot be equal to, or which the y values cannot be equal to, that is known as an asymptote. An asymptote is a line which a curve comes closer and closer to, but never touches it. Let's look at an example. So now let's look at an example. Here we have y equals 1 over x, and the graph of 1 over x, which with x ranging from -4 to 4. So you can see from the graph that as x approaches -infinity and +infinity, y approaches 0. And as x approaches 0, from both sides, positive and negative, y approaches positive and negative infinity. In the graph above, the domain is restricted by the fact that x cannot be 0. Division by 0 is impossible. So this is the denominator in the graph for the equation of this graph. The denominator cannot be equal to 0 because division by 0 is impossible. Therefore, x is not equal to 0 is a restriction on the domain. Since 1 cannot be divided by 0, there will also be a restriction for 0 in the range. You can see this from the graph that y cannot be equal to 0 because as the x values go to positive and negative infinity, y gets closer and closer. Y gets closer and closer to 0, but it never actually touches it. Therefore, there's an asymptote at y equals 0. You can tell this from the equation by substituting positive and negative infinity for x. What you get when you substitute that is you get 1 divided by a very large number, positive or negative. And 1 divided by a very large number, by an increasingly large positive or negative number, is increasingly closer and closer to 0. So there's an asymptote at y equals 0. The graph above clearly shows this because it gets closer and closer to the lines x equals 0 and y equals 0, but it never actually touches. So it gets closer and closer to the line x equals 0, which is the y-axis, and y equals 0, which is the x-axis. It gets closer and closer to these two lines, but it never actually touches them. So there's two asymptotes. One asymptote at x equals 0, which is the y-axis, and the other asymptote at y equals 0, which is the x-axis. Therefore, the domain is x belongs to all real numbers, but x is not equal to 0, and the range is y belongs to all real numbers, but y is not equal to 0. The asymptotes for this graph are x equals 0 and y equals 0. Be sure to visit our YouTube channel, MyMathEducator, for great videos, and like and subscribe for more great math videos. Also, visit our website, www.mymatheducator.com, where you'll be able to access our paid text lessons for a fee of $29.99 a year. If you want the same lessons in video format for free, covering the exact same content, head over to our YouTube channel, MyMathEducator. And now, feel free to click on the element on the screen to access the full-length lesson of the topic we just covered. Lesson 1, Functions, Domain, and Range. Alternatively, click on the playlist for the Grade 11 Functions course playlist. Happy studying!